And hello everyone. So hello, welcome back. We are going to continue talking about turbulence modeling, in especially the law of the wall. Okay, but before I carry on discussing something, I want to just clarify a potential confusion. Okay. Okay, I have this formula which we discussed in the last videos, and this actually came from the assumption over here, right? So now we see. So yes, we made this assumption that tau apparent and tau wall are pretty much the same, so that it is constant throughout this boundary layer region. Now, then we talked about a regime where the apparent what do you call that, shear stress is strictly due to the laminar regime, and then the other regime is where the turbulent shear stress, turbulent viscosity dominates, so that most of the viscosity, most of the shear stress, its apparent shear stress is caused by this turbulent viscosity. Now, if this shear stress, alright, let me draw here. Okay, go up. Yeah. If this, if let's say you have the wall here, and then okay, I'm saying that the shear stress over here, for example, or maybe the shear stress will be pointing this way, tau wall, and here is the tau apparent at the fluid. Right? So what we are saying here is that these two quantities are the same. But over here is, let's say, where you have lots of turbulence. Here is where you have no turbulence. So if that is true, how can these two be the same? Okay, so alright, how can these two be the same? Okay, so one way of looking at this is that, okay, indeed this apparent viscosity term actually changes from here to here. So here we have viscosity being just the fluid viscosity. Here we have the viscosity being the fluid viscosity plus the turbulent viscosity, right? So over here it looks like the apparent viscosity is higher. So what has to compensate? Well, the thing that has to compensate is this du dy. Alright, so in a place with a lower viscosity, you will have, like, you know, the linear law, u plus equals to y plus. So this will represent the du plus dy plus equals to 1, right? So this is for a fixed du dy plus. Over here, we have a du dy plus that is actually dependent. If you use a mixing length model anyway, you have a du dy plus that depends on y. So du plus dy plus equals to 1 over kappa y plus. Alright, so what changes to compensate for this viscosity change is this velocity gradient. So over here you will have this linear regime, then you will have a logarithmic regime that comes after in the turbulent sublayer. So that is how this shear stress here and this shear stress here is the same. So that when this viscosity changes, the apparent effective viscosity changes, the velocity gradient kind of changes to compensate for that. So that's why we have these two different regimes, and that's why you have a changing viscosity kind of thing. I mean, changing velocity gradient. Okay, so hopefully that clears things up in this law of the wall. Yeah, so this is the law of the wall. Okay, so hopefully that clears up the confusion. So we say that as the apparent viscosity changes, du plus dy plus changes to keep tau apparent constant. So that we can have the tau wall equals to tau apparent, because this velocity gradient changes as this viscosity also changes. Okay, so it changes to compensate for each other. Alright, so hopefully that clears it up. Yeah, so that we can have two regimes here. So the amount of shear stress is the same throughout, but the mechanism behind the generation of this apparent shear stress, it is different for different regimes. Okay, so yeah, hopefully that clears things up. Anyway, alright, so you have this very nice law that Van Driest model gives you for the law of the wall. So it will apply, I think, to y plus equals 300 or something like that. Okay, it cannot be all the way through, otherwise, you know, yeah, it kind of defeats the purpose of having CFD in the first place, or other, you know, the K epsilon model. Okay, so this applies to the turbulent region. Okay, now question is this. There is one small problem. While all of this is actually experimentally determined, and then this A plus, oh, I did not mention the value of A plus. A plus here, okay, A plus equals to 26. Yeah, A plus equals 26 is an empirical constant. No theoretical wizardry behind that. Or no, we're not deriving something new. Okay, so that is that. All right, so you have this very nice velocity profile that you can just manually calculate using some what do you call that? Software, doing some integration, numerical integration. Using kappa is usually equals to 0.4. A plus equals to 26. This is the Van Driest model. Now question is this, we have u plus and y plus, right? So we have a u plus and y plus, but then what is u plus and y plus? How do we get the velocity profile? We actually needed to scale it back, right? Okay, so I just want to remind you, you know, once we have u plus and y plus and y plus, we still need our ultimate velocity profile in the boundary layer, u versus y. Alright, and remember what our u star was, u plus was. U plus equals to u bar, which is the resolved viscosity, velocity, divided by u star. Yeah. So that is that, u bar over u star. Okay, and since we have this, we need to say, to find our u bar, we need to know what u star is. And what is u star? U star is the square root of the shear stress at the wall. Okay, u star equals the shear stress at the wall over the density, and of course you need to take a square root of that. Okay, so question is, what is this shear stress of the wall? Okay, and again, what has to be done is usually a series of experiments. Okay, we can find tau wall experimentally. Okay, so for example, let's say we have for a flat plate case, right? For flat plate case, we have this developing boundary layer, and then there'll be, after some time, after the Reynolds number gets big enough, there'll be turbulence happening around here. Okay, and then they made a what do you call that? They have a relation for the friction coefficient CF, the local friction coefficient, as a result of a Reynolds number. Okay, where this Reynolds number is Reynolds number is U infinity x over nu. Okay, x is the distance from, let's say, the start of this flat plate where the boundary layer starts. So over here we have some free stream. Okay, some free stream, and then it's meeting a flat plate. This is a classic flat plate flow example. And what then happens? We have CF, which is the friction coefficient. It will be put as a result of the Reynolds number. So, okay, for flat plate case, though these are simple cases, there are experiments that say CF x equals to 0.37 times bracket log 10 U infinity x divided by nu. Okay, and this is to the power of minus 2.584. So this is from experiment. We fit a curve to the data. Okay, we fit a curve to the data. This is from experiments. Okay, and then we get this sort of expression. And what is CFX? CFX equals to tau wall at whatever coordinate, x coordinate you have, over half rho u infinity square. Okay, so from experiment we have to fit a curve to the data, and for flat plate, the shear stress, when we do some data fitting, it can be related using this expression here, and this is valid from, okay, this is valid to Reynolds number equals to 2e5 all the way to 1e to the power of 1 to the power of 9, 10 to the power 9. So 2 times 10 to the power 5 to 1 times 10 to the power 9. Okay, and this is known as the Schultz-Grunow relation. So this is experiments that they have done. Okay, so especially good for turbulent flow. For laminar flow, another yeah. Okay, so okay, yeah. When is this turbulence actually when is this important? So usually the from this website anyway, the turbulent transition equals to, and it comes at the Reynolds number of 5 times 10 to the power of 5. This is the critical Reynolds number as shown by this website for flat plate flow. So actually I think, yeah, it's not 2 times 10 to the power of 5. I think it should be 5 times 10 to the power of 5 all the way to 10 to the power of 9. So this is just experimental data fitted for the turbulent region. Nothing too fancy there. Okay, so you can go and check check out the websites there. They will tell you what are the relevant important information. Of course, there are other forms of this. There are other forms of the shear stress kind of thing. Yeah, you'll see this coefficient over here as well. Slightly different correlation, but these are just data fitting to a curve. Nothing too big there. If let's say we have a pipe. Let's say we have a pipe or duct. Okay, then we use the Moody chart. What is the Moody chart? If you take a look at Paris Chemical Engineering Handbook, or I mean, you find it on some literature online. Okay, yeah, this is the Moody chart. Yeah, I took this particular one from Paris Chemical Engineering Handbook on Kindle, but yeah, you can also find it online. Okay, so this will tell you the friction coefficient for the turbulent region as a function of the Reynolds number and of course surface roughness. Okay, so we can see that the friction factor here equals to tau over, or tau wall over half rho U average squared. So notice that for this CFX in the flat plate flow, the reference velocity is this free stream velocity, but for let's say a pipe flow, the reference velocity is the average velocity or the superficial velocity. So that is the volumetric flow rate, or you can say, mass flow rate over, of course you want to get rid of the density, so you can have this. So it's the mass flow rate over density times area, and that will be the superficial fluid velocity or the average velocity. Okay, so mass flow rate over density times area. Okay, I'll just write that down. U average equals to mass flow rate divided by density and area. That is it. And okay, so that's the average velocity. Of course, this is just basically volumetric flow rate divided by the cross-sectional area. Okay, this is the cross-sectional area. Okay, so just to make it very, very clear. Okay, so this is great for most flows. I mean, in basic fluid mechanics, we have flat plate cases, we have pipe or duct cases, which is great. Question is, what about other kinds of flow? What about other kinds of flow? Okay, so definitely we cannot keep doing, I mean, ideally we want to do experiments for every kind of flow, not just pipe flow, duct flow, or flat plate flows. Okay, yeah, so yeah, we don't just want to do it for that kind of flow. We know there are lots of flow regimes in the whole history or purview or scope of fluid mechanics, so we still need a way to estimate them. How can we estimate this friction coefficient? So that's the subject I want to brush on slightly in the next video. Hopefully this video is clear as to where we get this friction coefficient and how do we get the shear stress, the wall shear stress from this friction coefficient. You can substitute that back in here to get U star, and then we get our velocity profile. Oh, this U star should be at the bottom, so we can get our velocity profile here. But at least you know that's the process that we go through, the thought process. We do experiments to find the wall shear stress, and then we should be able to get a suitable velocity profile. Okay, so and of course based on this, which kind of fits most experiments, and this is especially so for flows where we can assume this tau apparent being constant, then we can apply this one, and that applies for flat plate flows and to some extent duct flow as well. So so this is actually pretty good for most boundaries. So the only issue is to estimate the wall shear stress. So flat plate and duct flow, they have experiments, but how else can we estimate the wall shear stress? Yeah, then we can take a look in the next video. Thanks for watching. I'll see you guys again. Bye bye.